Professor Chow's Environmental Fluid Mechanics Laboratory. So clouds can be very inspiring. Why do we care about clouds? Clouds play a huge role in Earth's energy balance and weather, so they transfer heat and moisture and determine weather and precipitation patterns. Clouds also play a large role in climate, so clouds act like a mirror reflecting incoming solar radiation, which has a cooling effect on the planet. But clouds are also a greenhouse gas, so they trap heat radiated from the Earth, which has a warming effect on the climate. So whether clouds have a net cooling or warming effect on the climate depends on factors like the altitude of clouds in the atmosphere, their size, and their thickness. For instance, clouds that are very high in the atmosphere have a net warming effect on the climate, but clouds that are low in the atmosphere have a net cooling effect on the climate. And according to the IPCC, the International Panel on Climate Change's latest assessment report, clouds continue to contribute the largest uncertainty to Earth's changing energy balance and thereby climate. And research suggests that even small changes in the scope or location of clouds may change the climate more than or as much as anticipated changes due to caused by human emissions. So how do we learn more about clouds and predict their impact on the changing climate? We use climate and weather models, which approximate the atmosphere on a three-dimensional grid and solve for fluxes between grid cells and model small-scale processes that happen within a grid cell. But one of the challenges with climate modeling is achieving high resolution on a relatively coarse grid, because you can imagine that as you refine your grid, the computational power your model requires increases. And right now, some of the most powerful supercomputers in the world are running climate and weather models. So achieving a reasonably accurate result at coarse resolution is the objective of much modeling research. And my research focuses on simulating a particular cloud regime called marine stratocumulus. This is a lumpy sheet-like cloud that covers about 20% of the Earth's surface area at any given time, so it's critical to Earth's climate. In fact, we see it all the time in the Bay Area. This is a time-lapse taken at LBNL on the hill. And stratocumulus lies close to the surface, and it's often capped by an inversion. And an inversion just means that typically temperature decreases with altitude, and an inversion temperature increases with altitude. So you have warm air sitting above cold air, and since warm air rises, very little mixing is occurring at this inversion layer. This is a visualization of a simulation of marine stratocumulus. And again, you can see that there is cold, moist air capped beneath cool, dry air above, and very little mixing is occurring at this inversion layer, and that enables the cloud to persist. If mixing does occur at that inversion layer, then dry air would enter the cloud and moist air would escape upward and the cloud would evaporate. So marine stratocumulus is actually a very interesting cloud type to simulate because small-scale processes that are happening at cloud top actually determine the overall flow regime of the atmosphere. And this stands in contrast to most flow regimes that are determined by large-scale processes like large eddies driven by surface heating. So this makes marine stratocumulus a difficult but interesting test case to try to simulate. And I ran 3 simulations of marine stratocumulus and compared it to observations taken off the coast of California, and I focused on comparing 2 different numerical schemes for determining advection. So one is advection. Advection is transport, so this is a visualization of cloud water being transported or advected around the United States. This was just a morning about a week ago. So if you imagine that this is a grid cell in your computational domain, the moisture tendency due to advection would be the flux in minus the flux out. And there's different numerical methods for determining advection, and my research focused on comparing the default method for CM1, which is the cloud model that we use, with an alternative method, the WENO method, which has been shown to be successful in flows with sharp gradients. And since In our test case, there's a sharp transition at the inversion. We thought this would be an interesting method to test. So this is some of my results. These are horizontal cross sections taken at cloud top. So if you imagine that this is your simulation domain, this is a plane taken, that plane taken at cloud top, and the colors represent cloud water content, so blue being moist and red being dry. And this top one is my high resolution simulation. So this is like my reference to the truth because it's very high accuracy. It's very high resolution. It should be very high accuracy. And these two bottom ones are coarser resolution simulations. This one with using the default advection scheme, and this one using the WENO advection scheme. So you can see in the default, in the high resolution, that there's a lot of variability and very sharp gradients, but in the WENO, the cloud field has been smoothed, and this is an effect of the algorithm. So the smoothing of the scalar and vector fields by the WENO algorithm actually ends up to have a very influential impact on the overall simulation, which can be seen in this time series that depicts the evolution of the cloud field. So time is on the x-axis and altitude is on the y-axis, and the colors here represent cloud water content. So blue meaning no cloud present, white is a thick cloud, and red is the thickest cloud. And again, in the high resolution simulation, which is our reference to the truth, you can see that the cloud layer persists. And in the coarser simulations, the coarse simulation with the default advection scheme, the cloud layer diminishes slightly, but it still is maintained throughout the simulation, the 4-hour simulation. But in the WENO advection scheme, the cloud layer nearly completely dissipates by the end of the simulation. So the WENO scheme performed poorly and predicted incorrect dissipation of the cloud layer, when in reality the cloud layer was maintained. So in conclusion, my results and deeper analysis, which I don't have time to show today, indicate that marine stratocumulus is particularly sensitive to small-scale processes happening at cloud top, and the WENO algorithm smoothing near sharp transitions leads to artificially large mixing of dry air with the cloud layer. This led to incorrect dissipation of the cloud. So for marine stratocumulus and other flow regimes with similar characteristics, the default method should be used if accuracy is desired. So the question is whether the cloud persists or dissipates, and this changes everything from surface heating to wind patterns to precipitation and climate, and improved numerical simulation enables us to better predict the impact of clouds on weather and climate. I just want to acknowledge my mentor, Xiaoming Shi, and my professor, Tina Chow, in the SBUM thesis class. Thank you, and I'm happy to answer any questions.
I have a question on your simulation. You have your higher resolution, your lower resolution.
Yeah.
But is the higher resolution actually a simulation, or are those measurements through other instrumentation of that particular cloud scenario? I couldn't tell.
Yeah, so the high resolution is actually a simulation. So we simulated a domain with 5-meter vertical resolution for the high resolution, which is very high resolution. 5 meters, like global climate models are on the order of like 100 kilometers. So 5 meters is super high resolution. But we matched, basically validated it with observations taken from aircraft data. So there was a field campaign, yeah, exactly, off the coast of the Pacific with aircraft collecting data. So it closely matches it, yeah.
The first movie you showed, you called it a cloud, you described it like a cloud. But I think to most of us, this is the marine layer,
Fog.
known as fog.
Yeah, so fog, stratocumulus is actually just fog lifted off the ground. There isn't, I mean, really a cloud is just water, condensed water, right? Same thing as fog. And so typically we just call, condensed water that's near the surface fog, and when it's aloft, we call it a cloud. And so stratocumulus is a very shallow cloud, so it's kind of like elevated fog.
But the curious question, maybe you can explain it once again, I thought you gave an explanation, is what keeps the marine layer at that very well-defined level?
Yes, great question. So what's capping it right there is the inversion layer. And what that means is, okay. So what that means is temperature, right? Temperature decreases with altitude. If you hike a mountain, right? It's getting colder, there's snow on top of mountains. Temperature decreases with altitude. At the inversion layer, temperature begins to increase with altitude, and so you have warmer air sitting above colder air.
So the inversion layer is above the marine layer? Or
So this is the inversion layer right here, where you see where the clouds were capped right there. It means that warmer air is sitting above colder air, and since warm air rises, there's very little mixing happening.
Yeah. Very good. Local climate. Any other questions? If not, let me give you the honors.
Okay.